So last time we started with electrolytic conductance. See, in physics, you might have studied that a resistance which is offered by any conductor that is directly proportional to length and inversely proportional to area of cross section of the conductor. This is applicable to metals and electrolytic solution both. Now write down next paragraph. Like metals, electrolytic solutions also offer a resistance to the flow of current through them. This resistance is directly proportional to length and inversely proportional to area of cross section of the conductor. Now you have to copy from the board. That is R directly proportional to length, inversely proportional to area of cross section. Or I can say resistance is equal to a constant rho into L by A. Right? I'll rearrange this. Rho is equal to R into A by L. Label this equation as 1 and label rho. Rho is called resistivity oblique specific resistance. Rho is called resistivity or specific resistance. Now, how do we define it? It's very simple. Look here. If area of cross section is 1, that is unity. If length of the conductor is also 1, then resistance and resistivity will be equal. That will give us the definition of specific resistance or resistivity. Right on. Resistivity is defined as the resistance of solution placed between two electrodes of unit area of cross section placed 1 unit distance apart. Its units are ohm centimeter. Put that right down. Now I'll take the inverse of equation 1. Right down. Taking inverse of equation 1. It is 1 by rho, and the symbol for 1 by rho looks like small k, but it is not small k. This symbol is called kappa. This k, in fact, this is like this. This vertical line is a bit lengthy, and this is like this. I'll label it later. This is equal to 1 by R into inverse will be L by A. The symbol is called kappa, and This kappa stands for conductivity oblique specific conductance. So kappa is conductivity or specific conductance. If you remember, I told you units of rho are ohm centimeter. It means units of kappa will be ohm inverse centimeter inverse. Ohm inverse is mho. So mho centimeter inverse, or we can also say capital S. Capital S stands for Simon. Siemen. One Simon is one mho. So Simon centimeter inverse. This L by A, this is called cell constant. Why do we call it cell constant? That will be clear in the next topic. Again, when we define conductivity or specific conductance, we'll again take L and A equal to unity. So kappa will be equal to inverse of resistance will be conductance. Right on. Thus conductivity is defined as the conductance of electrolytic solution when it is placed between two electrodes of unit area of cross section which are unit distance apart. Its units are ohm inverse, centimeter inverse. On this basis, I'm sharing one numerical. Check your WhatsApp message. Numerical is in the video you'll find it as in text numerical 1, right? Calculate conductivity. Conductivity means specific conductance of the solution which offers a resistance of 120 ohms when measured in a conductivity cell in which electrodes are 72 centimeter square area cross section and placed 3.6 centimeter apart. So kappa will be equal to 1 by R. R is 120 into L by A. L is distance, that is 3.6 centimeters. Area of cross section is 72 centimeters square. Just multiply, divide, and you'll get the answer. This will be 4.167 into 10 power minus 4 ohm inverse centimeter inverse. Right? But remember, do not expect such simple numericals in the exam. Never. Next topic. Measurement of conductivity of ionic solutions. Measurement of conductivity of ionic solutions. Look here. For conductivity, that is specific conductance, formula is kappa is equal to 1 by R into L by A. So to find out the value of conductivity, that is kappa, I need three values. Resistance, which I'll measure by using Wheatstone bridge experiment. L and A. What are the values of L and A? That will be clear in this very topic. Right on. Resistance of electrolytic solution is measured by using Wheatstone bridge. bridge. Draw this. This is very simple for you because you have studied this in physics. R1 resistance 2, R3 is the resistance offered by electrolytic solution, which we want to measure. This is R4. You know, R1 and R2 are fixed resistances. R3 is the resistance which we want to calculate, we want to determine. R4, is variable resistance. And this is galvanometer in between. Right? So I think you don't need details at all. Right. Write the equation. R1 divided by R2 is equal to R3 divided by R4. Value of R3 is calculated. So this R3 is the value of R in equation 2. Now we are left with L and A. Right on. During the experiment, right on, there are 2 points. Number 1, alternating current should be used. During the experiment, alternating current should be used because direct current will lead to electrolysis and change concentration of solution Number 2, second point. For second point, look at me, listen carefully. See, when we carry out this experiment, we use a vessel which is called conductivity cell. In this conductivity cell, there'll be 2 electrodes which are fixed. We cannot take them out. They are fixed. Since these electrodes are fixed, it means area of cross section of these 2 electrodes is fixed. Distance between these 2 electrodes is also fixed. So values of distance between electrodes, that is L, is fixed. Value of area of cross section of electrodes is fixed. That is value of A is also fixed. Since the value of L and A are fixed for this conductivity cell, value of L by A is called cell constant, because this value will be fixed for a particular conductivity cell. So when electrolytic solution is filled in this conductivity cell, it will behave as a column of solution. It will behave as a column of solution whose area of cross section is fixed and length of the solution. This distance between electrodes is length of the solution, that is also fixed. Right on. Number 2, second point. Experiment should be carried out in a specially designed conductivity cell which consists of 2 platinum electrodes of fixed area of cross section within brackets capital A, and separated through a fixed distance within brackets small l. Due to this, solution placed between, due to this solution placed between these electrodes is a column of fixed length and area of cross section. Since values of L and A are fixed for a conductivity cell, L by A is called cell constant. Cell constant. Its units are centimeter inverse. Centimeter inverse. Next, two very small topics, both numerical based topics. First is molar conductivity. Molar conductivity. Within brackets, symbol is, this is capital letter lambda. This capital lambda. Symbol is lambda m, molar conductivity. See, in short, definition basically means total conductivity of all the ions produced by 1 mole of the electrolyte. I'll repeat. Total conductivity of all the ions produced by 1 mole of the electrolyte is called molar conductivity of the electrolyte. But in the definition, some additional thing has to be added, right? Right. It is defined as the conductance of all the ions produced by 1 mole of the electrolyte when its solution is placed between two electrodes of the conductivity cell which are 1 centimeter apart, and have such a large area of cross section, that the entire solution can be placed between them. Now just try to understand what's the meaning of such a lengthy definition, and what's the meaning of 1 centimeter apart, entire solution can be placed between them. Listen, strong electrolytes, they ionize completely. It means even if the solution is concentrated, it will completely ionize, it will completely change into ions. But problem comes when it's a weak electrolyte. Weak electrolyte ionizes partially, but ionization of weak electrolyte increases with increase in dilution. According to the definition, we have to consider all the ions produced by 1 mole of electrolyte. So keeping in mind that if it is a weak electrolyte and it has to be completely ionized, naturally its solution should be very, very dilute. And if the solution is very dilute, naturally volume will be very large. Definition says this entire solution in which 1 mole has completely ionized. This entire solution is placed between two electrodes of the conductivity cell, which are just 1 centimeter apart. They are very close, 1 centimeter apart. Then how can the entire solution be placed between them? Definition further says 1 centimeter apart and have such a large area of cross section of these electrodes that entire solution can be placed between these two electrodes, right? So this is the meaning of 1 centimeter apart, entire solution can be placed and whatnot. Now write down, mathematically, I'm giving the formula, mathematically, lambda m is equal to kappa into 1000 divided by molarity. You already know kappa is 1 by r into L by A. Units of lambda m will be ohm inverse, centimeter square, mole inverse. Ohm inverse, centimeter square, mole inverse. I'm sharing one numerical on this equation. Check your WhatsApp message. In the video, in the description box, you'll find it as in text numerical number 2. An electrolytic solution offers a resistance of 100 ohms when measured in a conductivity cell of cell constant 0.25 centimeter inverse. 400 cc of this solution is prepared by dissolving 4 grams of NaOH in water. First, we'll calculate molarity of this solution. Molarity will be 4 grams divided by molecular weight into 1000 divided by volume of solution. Volume is 400 cc. This molarity will come out to 0.25. Now, we are given cell constant and resistance. From this, we'll calculate the value of kappa. So kappa will be 1 by r. R is 100. L by A. L by A is 0.25. It will be 0.0025. Now, lambda m is equal to kappa into 1000 divided by molarity 0.25. So answer will come out to, let me check, answer will be 10 ohm inverse, centimeter square, mole inverse. This will be the answer. One more very similar definition. So write down next topic. Equivalent conductivity. Equivalent conductivity. Symbol lambda EQ. EQ stands for equivalent. See, the entire definition will be similar with the only difference that in molar conductivity, we considered 1 mole of electrolyte. In equivalent conductivity, we'll consider 1 gram equivalent of electrolyte. For this, you should remember the relation between equivalent weight and molecular weight. Molecular weight is equal to equivalent weight into n factor. Remember that. Anyways, it is defined as the conductance of all the ions produced by 1 gram equivalent of the electrolyte when its solution, remaining definition will be same, when its solution is placed between two electrodes of the conductivity cell, which are 1 centimeter apart and have such a large area of cross section that the entire solution can be placed between them. Entire solution can be placed between them. Mathematically, now write down the formula. Mathematically, lambda EQ is equal to kappa into 1000 divided by normality. I forgot to label these equations. I think earlier we had done equation number 1 and 2. Lambda molar conductivity, could label that at 3 and label this one as 4. So the only difference in these formulas is denominator. In molar conductivity, it was molarity. Now this is normality. That's the only difference. I'm sharing one numerical based on this equation number 4. Check your WhatsApp. Calculate equivalent conductivity of 1.2 molar solution of sodium carbonate if its specific conductivity is 14.4 into 10 to the power minus 2 ohm inverse centimeter inverse. So lambda equivalent will be equal to kappa. Kappa is 14.4 into 10 to the power minus 2 multiplied by 1000 divided by normality. But we are given molarity. For sodium carbonate, n factor is 2. It means normality will be molarity into 2. So normality is 2.4. Answer will be 60 ohm inverse centimeter square equivalent inverse. I think I forgot to tell you units of lambda EQ. Label that in equation number 4. Units are ohm inverse, centimeter square, equivalent inverse. Right? These are the units of lambda EQ, equivalent conductivity. Next topic. Variation of, next topic is variation of molar conductivity with concentration. With concentration. I'll repeat. Variation of molar conductivity with concentration. That is, if we change the concentration of electrolytic solution, how does molar conductivity change? Relax for a while, I'll explain. See, in electrolytes, I told you, charge is conducted by ions. It means more the number of ions per unit volume of the solution, more will be the conductivity. For this, again, think I told you last time that conductivity depends on number of ions, number 2, mobility of ions. So if the solution is dilute, number of ions per unit volume will be less. Therefore, conductivity, that is kappa, will also be less. But remember, as we keep on diluting the solution, although kappa keeps on decreasing, but molar conductivity keeps on increasing. Whether it's a strong electrolyte or weak electrolyte, molar conductivity will keep on increasing as we dilute the solution. If we keep on diluting the solution, it means denominator will decrease, value of lambda m will increase, and ultimately, when the concentration approaches 0, I'm not saying concentration is 0, is when the concentration approaches 0, or I can say at infinite dilution, value of lambda m molar conductivity becomes maximum. And this maximum limiting value of molar conductivity at infinite dilution. That is called this is called limiting molar conductivity, or this is also called molar conductivity at infinite dilution. These are two terms used. Now write down. Concentration. Yes, on decreasing the concentration, of electrolytic solution, conductivity means specific conductance. Conductivity, that is kappa, decreases due to decrease in number of ions per unit volume, which are the charge carriers. However, molar conductivity of strong as well as weak electrolytes increases with increase in dilution and approaches a maximum limiting value at infinite dilution within brackets. What's the meaning? Within brackets like this. This means concentration approaches zero. Remember, concentration is not zero. Concentration approaches zero. So I'll repeat, approaches maximum limiting value at infinite dilution, which is called limiting molar conductivity within brackets symbol lambda m naught, or there's one more term used, or molar conductivity at infinite dilution. For the second term, symbol is also different. Within brackets, write down symbol is lambda m infinity. So whether it is lambda m 0 or lambda m infinity, meaning is same, terms are different, symbols are different. In first term, 0, that is naught, stands for concentration is approaching 0. In the second symbol, infinity stands for dilution is infinity, dilution is infinite. Next paragraph. I'm giving you one equation. It's a totally theoretical topic, very small topic. Next paragraph. Variation of molar conductivity with concentration of a strong electrolyte. This is applicable only for strong electrolytes. Of strong electrolytes is given by the following Debye-Huckel-on-Sager equation. Given by the following Debye-Huckel-on-Sager equation. Now, what is this equation? Lambda mc is equal to lambda m infinity minus a into square root of c. labeled it equation number 5, although there's no numerical base on this topic, this equation. This is molar conductivity at concentration C. So C stands for concentration, this one and this one. Lambda infinity, M infinity, I already told you. Coming to A. For A, you'll have to write a couple of sentences. Write down. A is a constant. A is a constant whose value depends on the nature of electrolyte. That is depends on charges of cations and anions. On the basis of charges of ions, electrolytes are of different types. Electrolytes are of different types. For example, please copy from the board. For example, NaCl is 1,1 type, MgCl2 is 2,1 type. Now look at these two examples. I'll give you more example. In the type, I'm using two numbers. First number is the charge of cation. Second number is the charge of anion. Magnesium charge is +2. Chloride ion charge is 1 unit. Okay, 1 unit negative charge. So this is 2,1 type. One more example. Al2SO4 thrice. Aluminium sulfate is 3,2 type. Right? Further write down. All electrolytes of the same type have the same value of A. The value of constant A will be same for all electrolytes of the same type. You know, straight line equation is y is equal to mx plus c. In Debye-Huckel's equation, this is also a straight line equation. Now, how it is a straight line equation? This is y is equal to mx plus c. Right down. Equation 5 is a straight line equation with slope equal to minus a and intercept equal to lambda m infinity.
Sir, what is lambda m equal to?
Lambda m is molar conductivity. I'm saying lambda mc and lambda m infinity. Lambda mc is molar conductivity at concentration C, because this will change with change in concentration. This is y and this is x.
सर आई एम आस्किंग कि जैसे आपने स्लोप का बताया कि स्लोप माइनस ए है और दूसरा क्या बता रहे थे आप?
Intercept. Right. Now, in the next paragraph, I'm coming to something very important. This is a graph-based topic. It's in the same topic, of course, extension of that topic. Right on. Graphically, variation of molar conductivity with concentration of solution for strong and weak electrolyte is given below. It means when we change the concentration of solution, how does molar conductivity of a strong and weak electrolyte change? That I'm representing in this graph, and this will be a very, very important graph from examination point of view. This will be lambda MC versus square root of concentration. This line, this graph is almost parallel to x-axis. This is not parallel. This is almost parallel to x-axis. This is going downwards as concentration increases. This graph is for strong electrolyte. This graph is for weak electrolyte. Now listen to the explanation carefully. Dictation will take maximum 5 minutes. Look here. See, in both the cases, as we go from right to left means concentration is decreasing, or we can say dilution is increasing, right? So in both the cases, when dilution increases, molar conductivity increases. But the only difference is that molar conductivity of strong electrolyte increases slowly, increases gradually. But molar conductivity of weak electrolyte increases sharply on dilution. What is the difference? Oh, sorry, what is the reason behind it? In one case, increase is gradual. In the second case, increase is sudden or sharp increase. This is a very important question which generally comes in CBSE exam. This you'll be able to understand on the basis of number of ions and mobility of ions, if you remember I told you last time. See, when the solution is diluted, volume will increase. It means distance between cations and anions will increase. Distance increases means attraction between ions will become weaker. When attraction becomes weak, their mobility, their speed will increase, and that is why conductivity increases in both the cases. That is common. Now coming to number of ions. If we consider a strong electrolyte, it is completely ionized even if the solution is concentrated. So if we dilute the solution of a strong electrolyte, number of ions will not increase because it is already fully ionized. But when we dilute the solution of a weak electrolyte, its ionization will increase. That is, number of ions will increase, due to which conductivity will increase. It means I can say that in case of weak electrolyte, sharp increase in molar conductivity is due to two reasons. Number one, number of ions increases. Number two, mobility of ions also increases. Whereas in case of strong electrolytes, only mobility of ions increases, number of ions does not increase. One thing more, after that I'll start dictating. This is almost a straight line graph. Since this graph for strong electrolyte shows a trend, this graph can be extended. Extending the graph is called extrapolation of the graph. So this graph can be extrapolated. This is dotted line. Extrapolated to concentration approaching zero. And from the graph, from extrapolation of the graph, we can calculate the value of lambda m naught. Please extend this graph with the help of a dotted line in your notes. Label it. This is extrapolated graph. And here write down C approaching 0. So this type of extrapolation of the graph is not possible for weak electrolyte. Now write down, it will take maximum 5 minutes. As shown, lambda MC of strong as well as weak electrolytes increases with increase in dilution. Increases with increase in dilution. This increase is gradual for a strong electrolyte and sharp for a weak electrolyte, which can be explained as follows. Right, and next paragraph. On dilution, volume of solution increases, distance between cations and anions increases, attraction between them become weaker, so that mobility of ions increases. Full stop. A strong electrolyte is completely ionized even if the solution is concentrated, but ionization of weak electrolyte increases with increase in dilution. Therefore, on dilution, number of ions as well as mobility of ions of a weak electrolyte increases, but in case of a strong electrolyte, only the number of ions, only the mobility of ions increases. That is why molar conductivity of weak electrolyte increases sharply on dilution. Next paragraph, just about extrapolation. Since lambda mc, of a strong electrolyte increases gradually on dilution, its graph can be extrapolated to infinite dilution, and the value of lambda m infinity can be determined graphically. However, this is not possible for a weak electrolyte due to sharp increase in lambda mc with dilution. So that's all for today's class. Today, wait a minute.